All right, let's get started. So shaders, first of all, what is a shader? So in general, a shader is just a computer program that returns a color. So if you look at this picture here, what the shader is doing in this case is it's saying for these pixels around here, it's returning a white color. For these pixels around here, it's returning a blue color. And then for these pixels down to the bottom right, it's returning like a dark blue color. So in general, a shader is just a computer program that can tell you what color different parts of an object are. Now, the vast majority of shaders in games attempt to do realistic lighting, realistic enough lighting that looks good for a variety of different materials. There's been a lot of research effort put into this, trying to figure out what makes a good kind of universal shader that you can use for 95% of materials, that you can use for metals, fabrics, plastics, whatever. And so because of that research effort, most game engines actually come with a pretty decent shader called a PBR shader that works for most of the materials you would need. It's the thing your artists are usually working with. And as such, because it's already implemented in most every game engine, we're not going to talk about it. We're going to instead talk about other effects that we can't make using the standard material model. So these are three things that we're going to work on making today. So we have a holographic effect on the left, this ripple effect in the middle, and a fire effect on the right. For one reason or another, these are things that cannot be accomplished with the regular shader that comes with the game engine. You need to make your own shader to specify your own colors to make these things work. So first I want to check, does everyone have Godot and the project? If you open up the project, you should see, let me see if I can close this. Yeah, you should just see this gradient here, just a square with a gradient going left to right. Does everyone have this? Or if you don't have this, let me know. All right, looks like everyone is good. So let's start with this. Let's open up the project. So you see this gradient. So this is a very simple shader right now that just takes, that just gives you a particular color. It gives you a shade of gray depending on how far left or right you are. And let's look at how this is actually working. So on the left here, on the bottom left, you have all the files that are part of the project. Towards the bottom, you might need to scroll down. There's this thing called Plain 2D Shader. If you double click on it, you'll get this. You might need to use this thing on the right to move your view over to see the boxes over here. So this is a computer program. This is just a visual representation of a computer program. Instead of writing out code that says different operations to do, each of these boxes does a different operation, and we connect them together with these wires. So we say the result of this operation should be fed into this operation, and the result of that should be fed into the output. So you notice there's this output called color that rather expectedly tells what color to put on the screen. So whatever we plug into that socket is what is going to show up on the screen. So right now we're taking this input called UV, which looks weird. It's got this rainbow thing going on. UV tells us where on the square we are. And I'll get into how that works more in a bit. But suffice to say, we're taking where we are and we're getting just the X coordinate. So this works like coordinates do in math. So X goes left to right. You start at 0 here at this origin. And then as you keep going to the right, it increases and increases until you get 1. So if we take the X coordinate and use it as the color, we start with a color that is 0 at this X coordinate. We get to 0.5, so we get like a moderate shade of gray. And we get to 1, which is bright white. So here we use, we're just using the numerical value to specify the brightness of the color. So one thing we can also do, we can also look at the Y coordinate. So over here, instead of dragging this wire, or instead of having this wire X connect to the output, we can click and hold on the Y and connect it to the output. And you see, this is backwards from how we normally do it in math, but we get a very similar thing. We get the Y starting here at 0 and increasing as we go down all the way up until it goes to 1. What we can do with this is we can do different math functions to say that different things should happen at different X or Y coordinates. So if you look at, for example, this holographic effect, this looks kind of complicated, but it's actually just 3 simpler effects stacked on top of each other. And one of those simpler effects is this kind of window blind effect. We have parts of the image that are showing completely solid, but we have parts of the image that are completely transparent. So what we want in our shader is a way of saying, using the y coordinate to say, these rows should be solid and these rows should be transparent. The y coordinate lets us specify something that changes down over the plane. So what we're going to do, let's see. Before we get this window blind effect, we need just an image on the screen. So to get that image, what we can do is we can take on the left over here with our files. There's a file called gamedevicon.png, and I believe you can just drag this in. And it gives you this node that when you give it an appropriate coordinate, it'll give you back the color of the image at that coordinate. So instead of plugging UV into this first operation and plugging that operation into the output, let's plug UV into this new operation and plug the RGB output into our final output. So we now get the GameDev icon showing on the screen, but it's a little weird because we're not taking into account transparency. I'll describe a little bit how colors work here first. So what's happening is that this output, this RGB output, is telling us what color the image is at the particular coordinate. And colors are stored in a very particular way in a computer. They're stored using 3 numerical values. And these 3 values are enough to describe just about any color that we can see. But there's a 4th value that we're missing, which is called the alpha. If you click on this little eye icon, you can see what that looks like. You notice the alpha is 1 is bright white in areas that are solid in the original image, and is black, completely 0, at areas that are transparent in the original image. So this tells us where the image should be and where we should see the background instead. So what we can do, there's another output in our shader called alpha. So if we just connect the alpha of the image, the alpha of the shader, then we see that we correctly cut out the parts that we don't want. Before, if we had no alpha connected to the output, then we get this problem where everything is assumed to be solid. The alpha is 1 everywhere. It's completely opaque everywhere. But if we connect this instead, then we specify that these white regions where it's 1 should be opaque, but the black regions where it's 0 should be transparent. Is everyone following along so far, or is there stuff I should cover in more detail?
You're good.
All right, cool. So what we can do now, if we look back at the original effect, notice that some areas are completely transparent. Some bars are completely transparent, regardless of what the original image is there. So we want some math function that lets us turn those rows, the alpha at those rows, to 0. So what we can do is first we'll make a math function that has alternating bars of 1 and 0. Some regions across the screen will be 1, so like maybe this row across the screen will be 1 and the next row across the screen will be 0. And then what we can do is we can multiply that by the original alpha, because when you multiply anything by 0, it becomes 0. If you multiply anything by 1, it stays what it is. So this is a way of kind of cutting out the original alpha. Let's see. Actually, one way to really look at this before we get into it, if you click and hold on the alpha node or on the alpha output, but drag it into the middle of empty space and let go, it lets you add an additional node, so an additional operation. So in this search box, we can type multiply. And we specifically want this blue version, which multiplies a single value. The pink version multiplies 3 values at once. So when you're describing a color, which has 3 numbers at once that describe the entire color, you'd want to use this version. But when we're working with alpha, which is a single value, you want this version, which multiplies only a single value at once. So right now, it just multiplies this alpha by 0. So if we look at the result, we see that it's all 0. This little eye lets you preview what the output will look like. You can see if we change this to something like 0.5, now the black areas stay black, but the white areas have been reduced by 0.5. So this is a common theme in shaders, is that multiplication is kind of a scaling effect. It leaves 0 alone, but it gradually changes higher and higher values. So if we change this all the way up to 1, we see that it has no effect because anything times 1 is itself. So what we want is a way of multiplying by 0 for certain rows and multiplying by 1 for other rows. So let's just plug this into the alpha for now, and then we'll figure out what to plug in here. So this is where something like Desmos can be really useful. Desmos lets you play around with math functions and immediately see their results. Although I don't think it quite has what we're looking for now. So I'm just going to prototype this inside the shader editor. So what we want is something that changes based on the y-coordinate. Because for a particular row, the y-coordinate always stays the same. But if we go to the next row, then the y-coordinate is different. So if we take this y-coordinate, what we want to do is we want some way of making an alternating pattern with it. So this is where the, I believe it's called modulo in Godot. No, it's called remainder. So this is where the remainder function is really useful. Again, we want the blue version instead of the pink version since we are only working with one value at a time. If we look at the results of this, we see that I think nothing's changed. Yeah. So what the remainder does is it calculates the remainder after you do division. So if you take something and if you take this, which goes from 0 to 1, and you do the remainder of dividing it by 0.5, you notice that it increases and increases until it reaches a multiple of 0.5, in which case it resets, and then it goes back to increasing and increasing. So this modulo function is a really nice way of being able to repeat something over and over again. If you have an input that just gradually increases, like this y-coordinate, or later we'll also see time gradually increases over time, then this lets us chop it up into a repeating pattern, which is exactly what we want. We want this to have some repeating pattern based on the y-coordinate. But we want it to be a little more fine than that. We want more rows than that. So let's set this to a smaller number, like 0.1. And now it's really hard to see what's going on because unfortunately, one of the things about the remainder operator is that it doesn't do any scaling. So when it's chopping up into pieces, when I say remainder of this divided by 0.1, it starts at 0, goes up to 0.1, then it resets, goes up to 0.1, resets, goes up to 0.1. So the brightest part in this image is just 0.1. You see if I do 0.5, the brightest part in this image is 0.5. If I do 1, the brightest part in this image is 1. So a way we can correct for this is by scaling it up by 10. And remember that scaling is so if we multiply this by 10 and look at the result, we see that it's much better. So this now has a bunch of rows that go from 0 to 1 in a repeating pattern. So if we were to then multiply this by the alpha, we see that this kind of scales the original alpha. So the parts where this pattern is 1, we get the full original alpha. The parts where this is 0, we get full transparency. But this is not quite what we want because right now we have a gradual transition between 0 and 1. But what we really want is a sharp transition. So what we can do is we can use an operation that just tells us whether or not this particular value is above or below a certain threshold. So if you look at this, we're gradually transitioning from 0 to 1. If we put in a node, I believe it is called compare. Let me see. Let me see if it's called less than. So add a less than node. This will tell us if anything here is less than a particular value. So let's look at the result. You see that if we do something like 0.5, this image will only be 1. It'll only be white. It'll only be true when the input is less than 0.5. So you can see there's bands here where that is the case, where the original input is less than 0.5. So if we now plug this if we now multiply this by our original alpha, we get the effect we want. We got these nice sharp lines. I'm going to do a bit of reorganization here. So this is one part of the effect. We have these nice sharp lines, these like CRT scan line type things, but we want them to move over time. So just like multiplication scales a value, addition shifts a value. What we want is we want our input to be shifted over time. We want, for example, this row to be shifted up or down over time. So what we can do is we can shift the input. If we take this y coordinate and we shift it up or down, that's going to shift the entire pattern up or down. So since shifting is addition, what we can do is we can take this y coordinate, we add an add operation, and plug that into the rest of the thing. Now you see if we gradually tweak this, if we go like to 0.01, it moved up a bit. If we go to 0.02, moved up a bit more. And so of course we want to automate this. So one of the other inputs that shaders have available is time. And time is just a value that increases at a rate of 1 second per second. So let me add a time node first. So if you take this and you drag it off and add time, actually this is going to go pretty fast. If you're, I don't know, if you're photosensitive, don't do this stuff yet. So what this is doing now is it's taking time, which is the amount of seconds since the game engine or the game has been open, and it's adding it to the y coordinate. So now everything is acting like it's shifting over time, but it's going too fast. What we want to do is we want to scale time. We want to scale time to make it pass slower. So since scaling is multiplication, we drag off here and we add in a multiply. Where'd that go? And plug that into the add instead. So now we can scale it down to, say, 10% of its original speed. So 0.1 is 10%, and now that looks much better. So I'm going to reiterate this because it's really important. Having the multiplication and addition are just really essential operations in shaders. If you apply them to an input, it causes your pattern to be shifted by that amount or scaled by that amount. Apply them to an output, it causes the output to become brighter or darker if you scale it, or generally shifted up and down if you add it. In this case, since time increases, you can think of it as a line. You can think of it as a line on a graph. Actually, I will actually just use Desmos for this. So you can think of time like this. So this is what you get when you first use the time node. At 0 seconds from the start of the game, it gives you a value of 0. When 1 second has passed, you get a value of 1. When 3 seconds have passed, you get a value of 3. So if we take this and we multiply it, now we've found that we've squished everything down. We've scaled it. So now when we have 1 second passed in the game, now the result is only 0.1. Now when 3 seconds have passed in the game, the result is only 0.3. By scaling it, we make it change slower. We make a line change slower. We can think of the y coordinate in the same way because it works in the same way. So when we're 0.5 units down from the top, the y coordinate is 0.5. When we're 1 unit away from the top, the y coordinate is 1. And so if we do something like shift it, this way we're constantly shifting it up. Now everything is acting like it's at a different y coordinate. By adding this thing that is constantly changing, we're making it act like it's higher up than it used to be. We're making it act like it's a larger value than it used to be. We're making it act like it's a larger y coordinate than it used to be. And that makes the whole thing shift. Is everything making sense so far? I will take that as a yes. unless people have questions. Yours is blue. Interesting. Can you post a screenshot? I'm going to get some water real quick. I get dehydrated very quick. That is very weird. My guess is something is negative. Can you post a screenshot? Yeah, it does look kind of cool, actually. Can you post a screenshot of the lower part of the shader graph? Oh, I see. You're multiplying the, so this is what Solomon has. They have it in this order. There we go. So it's worth noting what's going on here because it's kind of interesting. So what's going on, let's see, let's set this to 0.05. We still have if we set this to like 0.1. So we're doing the comparison before we're doing the scaling in this case. So one of the things we could actually do, we could get rid of this scale, this multiplication entirely. I'm going to set it to 1 for now. And then I'm going to set this to 0.05. So what we're doing here is we're just accepting that the output of this ranges between 0 and 0.1. And so we can just directly say, find regions where it's less than 0.05. Only be 1 where it's less than 0.05. So that's another way to go about this. Instead of having this like multiplication by 10 in front and then being able to write 0.5, you can just do that instead. But if we have this scalar multiplication afterwards, what's happening is now this screen is not capable of showing it, but these bars are now not 1. Their value is 10 because the previous output goes from 0 to 1. But now if we multiply that by 10, it now goes from 0 to 10. So when we multiply this by the original alpha, now the values aren't 0 and 1, they're 0 and 10. So when the game tries to do the calculation, it's thinking that like when it's figuring out what colors things should be when they're transparent, normally alpha goes from 0 to 1. And that means like an alpha of 0.5 means it should be 50% your color and 50% the color behind it. If the alpha is 1, that means it should be 100% your color and 0% the color behind it, specifying that the alpha is 10. So now the game engine is a bit confused because you're telling it the color should be 1000% your color and negative 900% the color behind it. So you get this very weird effect. That is something you can mess around with to get some interesting effects. You can also do negative colors. So you can like plug in negative colors for lights, and when you shine them on things, they'll make them darker. Those are all like weird mathematical tricks you can do because the game engine is just doing math at its core. It's not checking that the math makes sense. So there's some weird things you can do with it like this. So I'm going to set this back to 1 and we'll get what we're looking for. So now there's a couple of other things we want to do. If we look back at this original GIF, this original prototype, One of the things we might notice is that this background color, it's a bit hard to see, but this background color is not pure black, it's a bit blue. In fact, everything looks a bit blue. This is a pretty tropey hologram type thing. For some reason, everyone likes it when their holograms are blue. And there's a couple ways you can do that. One of the ways is that you can multiply the color. So what you'll be doing is that you'll be scaling the amount of light that the color has. It's worth getting into here a bit more about how colors work. So what I'm going to do is I'm going to unplug this color, and I'm going to plug in something where we can manually put in numbers for each of the three components of the color. So I think it's called a it's called a vector compose. You want this pink one here, since we're working with colors which have three components. So get a vector compose and plug it into this color here. You can also enable the preview. So these three components here labeled X, Y, and Z. Usually vectors are used for storing positions in space. So they'll store an X coordinate, a Y coordinate, and a Z coordinate. But in this case, we're storing a color. So they're interpreted in a different way. This first one is actually how much red light the color has. So if you put a 1 in here, you'll notice that everything turns red. The second one is how much green light there is. So if this is 0, and wow, this is annoying, it's constantly scrolling. If I reset this to 0 and I change the second one to 1, now it's green because the second component indicates how much green light. And then finally, the third one indicates how much blue light. And because of a weird quirk of how humans perceive colors, you can represent just about any color that a human can perceive just by mixing together red, green, and blue light. So for example, if we wanted a nice hot pink, we could set the red to 1 and the blue to 1, and that gives us this very pink color. You might be familiar with this from games that have broken textures or things of the sort. This is that particular color. So what we can do is, since colors are just numbers, since colors are just lists of 3 numbers, we can do math on them to change what the color looks like. So one of the things we can do, if we take back our original color and plug that into the output, so we get this again. One of the things we can do is we can multiply each of those numbers by a particular value to make the color look more blue. So we can scale down the amount of red and green light and keep level the amount of blue light. So we can multiply the amount of red light by 0.5, multiply the amount of green light by 0.5, multiply the amount of blue light by 1, and the result will look more blue. So if we drag out here from the RGB and get a multiply, and this time we want the pink version, since we're working with lists of 3 numbers instead of just a single value, we want the pink one. So if we grab that and plug the result of that into the output, right now it's multiplying by 0, 0, 0. So anything multiplied by 0 is 0, so the result is black. But if we do instead 0.5, 0.51, you can click on this to edit it. Now we get a much more blue looking color. So the white has turned blue, the green has turned blue, but the black has remained black, which makes sense because it's the color where everything is 0, and so it stays 0 regardless of what you multiply it by. A different way of doing this, which you can change by simply going to this drop down and picking something else, is by adding a color instead. So instead of scaling everything, instead of scaling the amount of light, this will add in some blue light. So right now it's a bit bright, so the effect is a bit too strong. So I'm going to change this down to 0.1, 0.1, 0.2. Blue. So you see we get a different kind of effect. Right now the bright colors are kind of left alone, but the dark colors are affected most. This kind of makes sense because when you have black and you add these numbers to it, the result is going to be exactly this, because anything plus 0 is the original thing. So the black colors are going to turn into exactly this color, so they're going to look very blue. But when you have a color like white, which is 111, it's an equal mix of all the colors. When you add 0.1, 0.1, 0.2 to it, then you get 1.1, 1.1, 1.2, which is still pretty white. So it looks like, it still looks white. Both of these operations actually have physical interpretations. If you think about multiplication, it is like taking the original color and shining it on an object of a particular color. So if you think about, if you have a white light, 111, and you shine it on a red object, 100, then the result is going to be red. The fact that the object is red removes the green and blue light from the white light that you're shining on it. So the operation of shining a light onto a thing is multiplication. But if you shine multiple lights onto a thing, the colors add together. So if you think about like a projector screen, you have the light from the room that's making the projector screen kind of gray, plus the light from the projector. So everything looks kind of washed out. If you want that kind of washed out effect where the bright colors are very visible and very distinct, but the dark colors are skewed in some way, then you want addition. If you want to affect mostly the bright colors but leave the dark colors alone, then you want multiplication instead. Personally, I like addition best in this case. So I'm going to switch it back and do that. So now there's one other thing we need to do. This is waving back and forth. So that is a rather interesting effect we can do. Notice how this texture has an input. This is telling us where on the texture we want to sample the color from. So this pixel over here is sampling one particular region of the image. This pixel over here is sampling another region of the image. What the image is really doing is it's taking in a position and it's mapping it to a color. If we just look at the image asset, it's basically just a giant grid of colors. It takes in whatever position we're currently working with, and it gives us back the color at that position. So what we can do is if we want to make it wave around, we can modify the position that we're sampling at. We can modify the position we're plugging into it. So first we want to make a function that waves back and forth. And this is where sine is really handy. Because if we go back to Desmos, if we have our original thing and we apply sine to it, now our thing that used to just constantly increase now waves back and forth. So this is one of the things about shaders, is that it's really useful to know what all the math functions do and where they would be useful. If the more you work on shaders, the more you'll get an intuition of when things would be useful. So if we drag out from this input here, this input tells us where we are in the image. Now that we know how colors work, we can do a little bit of interpretation of what this is saying. The first component, when interpreted as a color, is the amount of red light there is. But when interpreted as a position, it's your x-coordinate. So you see, as we go from left to right, there's more and more red light because the x-coordinate gets bigger and bigger. As we go down, there's more and more green light because the second component is green, but it's also the y-coordinate. So as we go down, there's more and more y. And it just so happens that the mixture of red and green appears yellow to us. So in this corner where there's both a high y-coordinate and a high x-coordinate, they both reach about 1. That's where it looks yellow. So what we can do, we have this y-coordinate here. It's currently steadily increasing, and we can use this to get something that waves back and forth. Because if you look at our original prototype or our goal, notice how it's waving left to right. But the amount that it waves left to right is consistent across a particular row. So like this row, I wish I could pause this, but this is not a video. So this row is shifted a certain amount, and the row below it is shifted a different amount. So even though it's waving left to right, we want a value that changes top to bottom. We want a particular row to always be shifted the same amount, but we want different rows to be shifted different amounts. So we want to base our function on the y-coordinate. So what we can do is we can take our y, drag it out, and plug it into a sine, which unfortunately you have to dig a little bit for. It should be under scalar function sine. Again, I think there's a pink version. Yeah, we don't want the pink version. We want the blue version since we're only working with a single value. So we can look at the little eye to see what this looks like. And we notice right now, it's not actually doing that thing we want. It's not actually cycling back and forth. It's just steadily increasing like the y-coordinate. And the problem is that if we look at our function here on Desmos, right now we're just plugging in a number between 0 and 1. And so you can see sine in between 0 and 1 just kind of steadily increases. It doesn't really do anything interesting. What we want is something that moves like this. So we need a bigger input. So if we want an input between 0 and 1 to act like it's really going in between, say, 0 and 15, that's a multiplication operation. So instead of doing sine of x, we can do sine of 15 times x. So now if we zoom in between 0 and 1, it's cycling back and forth several times because now the input is acting like it's bigger, scaled up than what it used to be. So we can do that here in between the sine function and the y coordinate. We drag off from the, no, Guido, please. There we go. Drag off from that, get a multiply. And plug it into the sine. Right now it's multiplying by 0, so it's doing the opposite of what we want. But if we multiply by 15, we see that we start getting what we want. This image looks different from what we got on Desmos, because if you notice on Desmos, it goes negative, and computer colors only go between 0 and 1. Anything above 1 gets clipped to 1, anything below 0 gets clipped to 0. So you see the parts of the function that should be negative are just showing up as 0. But that's actually okay for what we want, because what we're going to do is we're going to use this to shift the coordinate left and right. And so it's perfectly fine to shift it by a negative amount. Yeah, I'll get into that in a bit. But first, let's just get it cycling a good amount of times. I think 15 is not enough. We're only getting like 3 cycles here. So let's change it up to something like 30. And that looks better. So what we can do, now what we want to do is we want to shift the x coordinate that we're using for the image. We want a particular row to act like all the x coordinates have been shifted in one direction. So that'll give us that wobbling effect. So what we can do, if we take our UV coordinate and drag off it, we want an addition. And this time we want the pink version, because this is a coordinate. It has up to 3 values in it. Right now we're only using the x and y components. In 3D shaders, it also has a z component. So we want to use the pink version to operate on all of those at once. So you notice if we take this addition and we plug it into the UV, let's just play around with this a little bit to get an idea for how it works. If we add like 0.1 to the x, notice how everything gets shifted to the left. If we add 0.3 to the y, everything gets shifted up. So again, since addition is shifting, this is the exact operation we want. What we want is for some rows to have their x-coordinate shifted to the left and have some rows have their x-coordinate shifted to the right. And so that's why it's okay to have negative values here, because if a positive value shifts to the right, then a negative value will just shift to the left. So what we can do here, first we'll need to turn this into a vector, because right now we just have a single value and we want to turn it into one of 3 values. So drag off from the sine function and get a vector compose. You have to spell it all as one word or it won't recognize it, unfortunately. So vector compose, this lets us turn 3 separate values into a vector, which is a bundle of 3 values. So just plug this into the x because we want to shift the x coordinate using this value, and then plug the result of that into the addition. And right now, that is way too much, because what's going on here is this ranges from 0 to 1. This image accepts inputs from 0 to 1. So right now, our sine function goes between -1 and 1. So it's shifting the entire width of the image back and forth. So we get this very distorted effect. So we want it not to go in between -1 and 1, but maybe in between -0.1 and +0.1. So that's a scaling, so we want addition. We want multiplication. So drag this off so we have some room. In between the sine function and the vector compose, we want a multiplication to scale it down and tame it. I apologize, I'm not sure why it's constantly jumping around. anyone knows how to make that not happen, please let me know. I'm going to check if there's anything up here. You know. Okay, so multiply. Right now we're multiplying by 0 by default. So now we have no translation, which is clearly not what we want. Try 0.1, and that's still a bit too much in my opinion. So we can play around with values here until we get something that looks right. That's not enough. I think that looks, that'll be fine for now. This is one of the things about shaders is that you'll spend much time tweaking it to get it just right. I could spend quite a bit of time doing that. So one final thing we want is we want to do the same thing that we did with these vertical bars. We want to make this wavy effect move up and down over time. So we do that the same way we did before. We add the Y component using time. So I think, let's just reuse what we have here. In between now it's your call whether you want to do it in between the Y coordinate and the multiply, or if you want to do it in between the multiply and the sign. The effect is that if you do it before the multiply, whatever you add to it will automatically get scaled up by 30. And if you do it after the multiply, it will not automatically be scaled up by 30. So I think I'm going to do it afterwards, because if we don't scale it up by 30, that's going to be slower. And I think I want a slow effect in this case. So here with the multiply after the Y, drag it off and get an addition, again, the blue version. And add our time value that we scaled earlier to be smaller. And take the result and plug it into sine. And now I think that is moving very slowly. Okay, so what I'm going to do to make it faster is instead of plugging in this scaled value, I'm going to plug in the full-on value that is not scaled down by 10%. So there we go. Now we get this kind of wavy effect. If you want, you can add another multiply in between the time and the addition to tweak how fast this wavy effect is going. And I believe that is it. I do have a finished shader that we can look at. So in the bottom left, there's 3 files: finished fire, finished hologram, and finished ripples. So those are the shaders that we are going to implement. Those are the ones that I tested out to make the final images on the slideshow. Oh, one of the things we didn't do is that in this shader, I took the alpha and I multiplied it by 0.5. So what that does is it scales it down by 50%. So now instead of everything being either fully opaque or fully transparent, now everything is either fully transparent or 50% transparent, which is closer to how a hologram really works, or is thought to work. So that is the hologram effect, basically. Are there any questions on this part? Let me see if someone is typing. Okay. So the horizontal pan, what you do is you take this coordinate. This originally was telling us where to look up on the image. So it's like, yeah, it tells us where on the image we need to look to find the particular color. So we can offset this using an addition, because since addition shifts things, and we shift it by something that's waving back and forth. So do you need the addition part, or do you need the part of what we're adding to it? Okay. Yeah, so we just take that thing that we made, that cycling sine pattern that just goes like this, and we plug it into a vector compose so that we just say we want to shift the x by that amount. We don't want to shift the y and z. And we use that to correspondingly shift the input to the image. Does that answer your question? So for this, the plane comes with this UV input. The way UV works is it's something usually that the artist makes. It's a way of saying, because for 3D objects, we really only care about their 2D surface. So a UV map is a way of saying, I want this 3D part of the object to be mapped to this 2D region on an image. So using the UV input in the shader just says where on the image the current pixel should be according to the UV map. So for a plane, it's very simple. It's just the top left corner should be the top left of the image, the bottom right should be the bottom right. All right, and so now we're going to move on to make another shader. If you want, you can save this as, oh wait, no, that's going to be a problem. If you want to go back, you can look at one of the finished effects on the left, but for now we're going to take all of this and delete it. So click and drag a box over everything except the UV input and the output. So drag it over everything and press delete. So we should just have this now. So we're going to make this ripple effect. So this looks very similar to the hologram effect where we had horizontal bars moving up, but now we have circles moving out. So just like in the hologram effect, we had something that we used the Y component because it changed as we went from top to bottom, and then we picked out certain regions of that to make horizontal bars. Wait, show how we moved what? Oh, the shader. In the bottom right, you can click and drag here, and then you can click and drag on these to move them around. Okay. So since we wanted horizontal bars, we wanted something that stayed constant over a horizontal region, but changed as we went up and down. So we wanted the Y coordinate. But here we want something that stays the same when we go in a circle. When we do this region, we want the value to stay the same, but as we go away from the center, we want it to increase. So what we want is basically the distance from the center. What we can do, if we take this, since this is a coordinate, we can find its length or distance. So if we just take this UV input here, drag off and do I think it's length. Yeah. Add a length operation and look at what that looks like. This is almost what we want. This starts at 0 in the top left corner and it increases as we go farther and farther away in a circular fashion until this does actually increase past 1. It's just that the monitor can't show any colors past 1, so it looks like it's all the same color. But really it's continuing to increase. If we plug this into the color output, we could see what it looks like on our plane. But this is not exactly what we want because we want the ripple to emanate from the center of the plane. And so this is again a shift, so we want an addition. So if we take the inputs and we make an add operation, and we want the pink version since we're working with a coordinate instead of a single value, and plug that in. Now what we want to do is we want to add, you might think you would want to add 0.5, 0.5, but that actually does the opposite of what we want. What we want is negative 0.5, negative 0.5. And I'll do a little bit about why that's the case. So think about this pixel in the center. If we don't do this add operation, actually, is there a way to mute this? No. Okay. If we don't do this add operation, the UV input tells us that this pixel in the center is at 0.5, 0.5. But we want it to act like it's in the center. We want it to act like it has no distance. So we want it to act like it's at 0, 0. So to move 0.5, 0, we subtract 0.5 from it instead of adding. So now we got this length. Now we can do fancy stuff with it. So we can do the same thing we did before with the sine to make this cycle back and forth. Sine and remainder are both ways of making stuff cycle back and forth. Let's see. Get a sine, plug that into the output. And we have the same problem we have before where the input is not big enough to get the cycling effect of sine, so we just need to make it bigger. We need to scale it up, so we need to use a multiplication. I'm going to start going faster, so let me know if I'm going too fast. So we scale it up by 10, that's not enough. We scale it up by 100, that's about right. Wait, why is it doing... Oh, sorry. I added an extra 0.5 here. There should be 0. There we go. So now we've got this kind of ripple pattern. Oh, damn, that's a lot of people. So now we want it to move out from the center. So we can use the same trick we did before. We want to shift everything by a time value. We want to shift it so that as time goes on, these regions, these rings, act like they're farther and farther or closer and closer from the center. So let's just do, I'm not sure whether we'll need to add or subtract time. This is something we can try it, guess and check, and see what works. This is computer science. We don't need to be exact. So add and add in between the length and the multiply. Like that. So now you can see if we add like 0.1, everything gets a little bit bigger. Add 0.2, everything gets a little bit bigger. So I'm going to prematurely add a multiply so that we can scale time right away. Set this to maybe 0.1. So now this value will increase at a rate of 0.1 per second, and then we add in our time. And as you can see, it is in fact backwards. So the way we fix this is very simple. We just make time go backwards. So instead of multiplying time by positive 0.1, we multiply it by negative 0.1. So now it decreases by 0.1 every second. And now we get this ripple effect going outwards. But now it would be kind of cool if we could apply some pattern to these ripples. Because if you look at here, I just have a very simple pattern going on. Some of the rings are brighter, some of them are darker, and you notice there's only like 5 of them. So what we can do, if we want to, like previously we used an image to convert a position to a color, but textures are very, very general. We can use them to convert any kind of input to any kind of output. So what we can do is if you look at this, which one is it? Rings.tres down here, you'll notice it's this little curve thing. So this is also a texture. This is taking a single value input and it's producing a single value output. So it starts at 0 and it outputs 0. At like 0.1, it outputs something higher. At like 0.2, it outputs 0 again, and so on. And then outside this range, it just outputs nothing, or it outputs 0. So if we go back to plain 2D shader, we can drag rings.tres, and we got this texture now. So we can use this texture to control the color of the rings. But first, we're going to need something to input into it. So to get that, if you look at this here, you'll notice the pattern moves out as the rings move out, but also it repeats over time. So what we want is something that we want length that increases as we go out, but periodically cycles. So if we go to Desmos, we had sine. This is nice for waving back and forth, but what we really want is, in Desmos it's called mod, in Godot and some other things it's called remainder. So if we do something like this, this is what we did before to get the window blind effect. This value just cycles in between 0 and the maximum we put it up to. And then once it reaches that maximum, it wraps back. So this is exactly what we want here. We want the length to increase and increase, or we want the place we look up the texture to increase and increase, but then at some point wrap back the original thing. So what we can do is if we look at our, let's see, which one is it? Yeah, if we look at our output here, this is not really showing anything right now because we are using a negative scaling on time, so everything is below 0. But what we can do is we can apply the remainder function, and we should get something close to what we want. Let's see. Let's try 1. And so you can see this is exactly the sort of thing we want. We want some kind of pattern going out from the center, but that repeats over time. So if you think about this value, let's just actually plug this into the output for a second. This is also something we can plug into a texture. We can give a texture this number, and it'll give us a corresponding number. In our case, this texture we have here is one-dimensional, so it just takes one number and outputs one number. So these pixels here will use the value at the end of the texture because they're 1. These pixels here will use the value at the start of the texture because they're 0. So this will slowly cycle between using the end of the texture back to the start of the texture. So we can plug that in here to the input, and let's just look at what the texture outputs in this case. So now you see we got this interesting pattern. This pattern is exactly provided by the texture. So if we click on this, we can tweak this to tweak the pattern. So I can move this around, I can move this peak, stuff like that. And so what we can do is just like we did with the window blind effect, if we multiply this by our original, by our simple ring pattern, this will scale some of the rings to be the same brightness, but it'll make some of the rings darker. So specifically, one of the things you'll notice is that when we plug this directly into the output, we're only getting a red value. So we want to extract that red value first. So we just have that thing and nothing else. So on the RGB, click and drag and do a color vector decompose. All one word again. And so this will let us get, it calls it the X, Y, and Z coordinates, but in this case, they're really RGB coordinates. So if we get just the X value and we multiply it by our ring pattern to scale it, there we go. We now have that kind of effect. One thing left to do is that this is actually, this is just outputting a color right now, but if we look at this, we can actually see the background through it. So the way we do that is with the alpha. So instead of plugging this into color, we can plug this into the alpha and use something else to specify the color. So we have this as the transparency now, and then the color, we can just plug in a vector compose to pick whatever color we want. So I'm just going to do white here. Oh, wow. That is not what I expected. Oh, we're having the same problem that Solomon was having. Some of the alpha is negative. So the way we solve this, unless you want this effect, the way we solve this is with something called, I think it's either called, it's called clamp. So what clamp will do is it'll take a value that ranges between any range you want, and it will clip off anything below 0 to be exactly 0. It'll clip off anything above 1 to be exactly 1. So it's really useful for solving these kinds of problems. This one in particular actually lets you set the upper and lower bounds. So if you want to clip off everything in between 0 and 0.1, for example, you could do that. And so there we have our effect. Now you could do a bunch more fancy stuff with this. Like you could change the color based on which ring you're in. Like one of the things you could do is you can make 3 more of these textures to specify the red, green, and blue components of each of the rings and have some variation that way. Or you could do some fancy math function. Like you could do some, you could take the UV coordinate and do some sines and cosines to make a weird wavy pattern of colors, all kinds of things. But that's it for this particular shader. So I'm going to move on to the last one because the last one has a really important effect in it. well, first of all, are there any questions on this ripple effect? All right. I see no one typing, so I'm going to assume everything is fine. So this last one is really important. Right now, we've been using a lot of rigid math functions, and math functions are great for getting these kind of surgical, crisp effects. But in real life, things are not so clean and simple. So a really great way to emulate some of that is with this thing called Perlin noise. So I'm going to contrast this with, you might have seen pictures of like TV static before. So this is what happens when you pick a purely random number for every pixel on the screen. This shader just generates a random number based on which pixel or which position is currently being rendered. But this is not really good because it's too fine-grained. And then the math functions we had before are not good as well because they are too coarse. They're too predictable. So we want something that's kind of a mediary in between. And so that's where Perlin noise comes in. Perlin noise is technically random in that if you pick 2 points that are very far apart, if you pick like this point and this point, they'll be very different colors. But crucially, if you move only a little bit, the values, the pixels that are close to each other have similar values. So like this pixel and this pixel are very similar to each other. They're both a similar shade of black. Put another way, Perlin noise changes slowly as you slowly change the inputs. So let's go into our shader. Let's delete everything again and start working on this fire effect. Because this fire effect is based on Perlin noise. You can, if I toggle back and forth, you can kind of see some of the similarities. The kind of wavy pattern of the fire looks kind of like the wavy pattern of the Perlin noise. So you should hopefully have, if I've set up everything correctly, an extra node in this project that is not usually available in Godot. If you take the UV coordinate and you drag off from it, you should be able to add a Perlin noise 3D node. So go ahead and add that. Oh, it doesn't automatically connect. Okay. And if you view the result, you see this looks exactly like what we have on the slide. So plugging this into the output, we just get that on the output. So first things first, we want this to look, or we want it to have the color of fire. So you notice in certain regions it's white, in certain regions it's orange, in certain regions it's red. So there is a gradient called kind of fire in the project, which exactly does this. It's a gradient that it's another texture. You put in a number. Low numbers go to red, medium numbers go to orange, high numbers go to white. So if we use this texture in between our Perlin noise node and our output node, then the Perlin noise gets transformed into this orangey red Perlin noise. So I'm going to plug this into the input, plug the output into the output. Oh, this is another way that you can assign colors to the rings in the previous example is by using a gradient texture. So if you want to, you can tweak this this gradient texture to get a different effect. You can make like a fantasy fire effect where you get like blue and green, get something weird like that. But there's a couple things we need to do now. First of all, it moves, but we're going to get to that a little bit later. What I'm going to do right now is address the transparency. Some of these regions are transparent. The fire fades over time. So what we want is not only to use just this color, we also want to use this Perlin noise to adjust the transparency. So we can just very simply plug the output of the Perlin noise into the alpha. And it looks a bit weird right now, but it'll look a bit better once we have it in motion. So you can see some of the regions are darker because they're showing through to the background. Some of the regions are brighter because they are using the color we're outputting. So another thing is that it fades as it goes up in the image. Notice that there's a lot more transparent regions up here versus down here. And so what we want is we want to shift everything. We want to have the top region shifted so that a bunch of it is completely transparent. but we want the bottom region shifted so that it's mostly opaque. So since we want to do a shift, we want to do addition. We're going to add an addition here in between the Perlin Noise 3D and connect the output to the texture and the alpha. So if we add like 0.5, notice how everything gets brighter. If we add like negative 0.5, notice how everything gets darker. Since this is technically producing negative values, I'm also going to add a clamp here just to make sure the alpha works correctly. But you don't need to do that on the texture. The texture will handle that kind of stuff for you. So you can notice in the output here, you get this very nice effect. If we do like negative 0.3, actually, let me do something more extreme. You get like this shrinking effect because all the parts of the image that were below 0.4 are now crushed to 0. And only the stuff that was above 0.4 remains as visible. So this is kind of what we want in the fire. We want the flames to slowly shrink over time, or slowly shrink as they rise up. So what we want then is something that will shrink the values that are higher up in the shader and blow up the values that are lower in the shader. So we want something that is low up here and high down here. So we can use the y coordinate. So with the UV coordinate, drag off an output. It's a vector decompose, again, all one word. And we'll use the y coordinate. So this will make the lower regions more solid. This will make the brighter regions. Right now, the higher regions will just stay the same because adding 0 to anything leaves it alone. So we get this effect. This is partially what we want, but we need to shift everything a bit more. Right now we have the top is kind of solid and the bottom is just completely washed out solid. What we want is the top to be lower and the bottom to be lower as well. So we want to shift everything. So we want to add an addition, specifically in between Y and this over here. So add an addition, plug it into here. So this will let us shift. Everything. If we enable the preview, if we do like negative 0.5, now we get something looking very good. Because what's going on here is this used to go from 0 to 1. Now by subtracting 0.5, it's now going from negative 0.5 to positive 0.5. So these regions at the top are getting cut out. They're getting reduced. These regions at the bottom are getting blown up. They're getting increased. And finally, we want to animate it over time. So there's two things going on here. First, everything is rising over time. So let's just add something let's do the same thing that we did in the holographic shader, where we take the y coordinate, or we add something to the y coordinate. In the hologram shader, we were shifting left and right, so we wanted to add to the x coordinate. But in this case, we want to shift up and down, so we want to add to the y coordinate. So drag off from the UV input and get another add, this time the purple version, because we are working with a coordinate. And you notice if we plug this in appropriately and mess around with the y value, if we add like 0.1, everything moves. So same thing as before, we want to run a time into a multiply to scale it, into a vector compose to specify that we're only using it for the y coordinate, and run it into this vector add. So we're gonna do that backwards because that just makes it easier for navigating the menus. So vector add gets the results of a vector compose. The y is going to be the result of scaling the time, so it's going to be the result of a multiply. Oh, come on. There we go. We're going to multiply maybe by 0.1. I really wish it didn't move. And the other thing we're multiplying by is, of course, time. So now you see everything is slowly rising over time. And as it gets higher, the flames gradually shrink and disappear. So this is almost what we want. Let me increase this a bit. So this is almost what we have going on here. But it's a bit hard to see. The flames are also warbling in a weird way over time. I want you to notice that this Perlin noise, it doesn't only have an X and a Y input, it has a Z input. So just like in our 2D example, where when you change the X or Y a little bit, the output only changes a little bit, with 3D Perlin noise, it does much the same thing, but it adds a Z component. So if you change any of the X, Y, or Z a little bit, then the output changes a little bit. But if you change them a lot, then the output changes a lot. But critically, there's nothing forcing you to use an actual coordinate, an actual XYZ coordinate as the input. You don't actually have to use position as the input like this person did. You could use something entirely different for the Z input or any other input. In this case, we're going to use X and Y as a position, but we're going to use Z as time. So this way, the Perlin noise is going to change slowly for small inputs or for small changes to X and Y, but also for small changes in time. So that's going to result in a weird shifting warping effect. So let's take this result of multiplying time by 0.2 and plug it into the Z component of the Perlin noise. And now if we zoom in specifically on the preview of the Perlin noise, you notice not only is it shifting up over time, but it's gradually morphing over time. So small changes in time result in a small change to the Perlin noise texture, but a large change in time results in a large change to the Perlin noise texture. And that is the conclusion of the fire effect. If you want, you can tweak these things to have it go faster or slower in different ways. You can have different speeds for the warping effect versus for the shifting effect. You could also add some shifting back and forth with the like with the hologram to make it look a little more windy. One of the other really useful properties of Perlin noise, or useful use cases of Perlin noise, is to distort an image. So just like we used a sine function to distort an image in the hologram case, you could use the output of a Perlin noise function to distort an image, and you get this kind of mirage effect. And with that, that is about all I have. Is there any questions about this or anything else? All right. I do not see anyone typing, so I will assume there are no questions. All right, well, thank you for coming. I hope you learned something interesting, and I will see you all again some other time.